In a previous lecture, we learned some weird facts about electrons. For one thing, we learned that electrons have both wave-like and particle-like properties. The particle-like properties are more familiar and easier to think about, include the fact that electrons have mass and they can be gained or lost from an atom. Both of these indicate that they're a solid particle that acts as an individual unit. However, electrons also have wave-like properties, and the primary evidence for this that we discussed is the fact that electrons exist in discrete quantum levels. These levels are often shown as rings around an atom, as in the Bohr model on the upper left. But we can also think of these discrete quantum levels as waves, and an electron wave isn't like a wave on water that's linear. Instead, it's kind of like a circular wave, and the wave must join together or connect to itself. And each place that this can happen is a quantum level that the electron can exist in. Outside of this area, where a wave can't join to form a perfect circle, the electrons can't exist. Okay, so we know that electrons exist in quantum levels, and the particular place that an electron exists is called an orbital. This is a mathematically defined space in which an electron is most likely to exist. And I'll go into a little bit more detail about what I mean by that as we continue, but this is the way the location of electrons is described. Okay, electron arrangement is defined by the following parameters. There's a principal quantum number, or principal shell, which is those rings that we saw in the Bohr model, and they're usually described by the letter n. So there's n equals 1 is the ring closest to the nucleus of the atom. Then there's 2, 3, 4, all the way up to shell 7, which is the largest. Within each principal shell exists one or more subshells. Subshells are indicated by the letters S, P, D, or F. And again, we'll go into that in more detail what that means, but for now, you just have to realize that within each principal quantum shell, there are a bunch of one or more subshells. And then within each subshell, there's one or more orbitals. And the orbitals are the actual places where the electrons exist. So one way you can think of this is that the orbital is kind of like, if it was an address, it's a house number, and the orbital is like the house that the electrons reside in. Then we have the subshell, which is like the street, and the principal quantum number, or principal shell, is like the city. And you need all three pieces of information to find out where the electron is, right? If you have a house number, but you don't know what street, you're not going to be sure which house it's on. And likewise, there might be a street, like if you're at 100 Main Street, you need to know which city that is in, because like a lot of cities have a main street. So you need all three pieces of information, and the information can have slightly different meanings too about, for example, like a house number that's in one city, the house might be larger or smaller or have different properties. So it's the same with electron arrangement. So the orbitals vary slightly depending on which principal quantum number or quantum shell they're in and which subshell they're in. Okay, so once again, I'm going back to the principal shells, which are labeled 1, 2, 3, 4, and then here I just have greater than 4. They go up to 7. And these correspond to the rings in the Bohr model of the atom, shown below. For each principal shell, it can have a certain number of subshells. Now, if you look here, principal shell 1 only has one subshell. Principal shell 2 has 2 subshells. Principal shell 3 has 3 subshells, and principal shell 4 has 4 subshells. So it each one has one more subshell than the last, but this changes. Once we get to 5, 6, and 7, they only have 4 subshells. There are no more subshells than that. All right, now the kinds of subshells. These vary as well. There's 4 different kinds named S, P, D, and F. And unfortunately, I know these are kind of hard to remember. These names were given before they really knew what these subshells were. So they really don't have like a whole lot of meaning right now. But just know that the principal shell 1 has the S subshell only. Principal shell 2, now it has 2. It has S and also has P. 3 has S, P, and D. And 4 has S, P, D, and F. And then above 4, there's no more subshells beyond F, so all the other 5, 6, and 7 all have S, P, D, and F subshells. So if you look here, every single principal shell has an S subshell. Then shells 2 through 7 have P as well, and then shells 3 through 7 have D as well, and then 4 and above have S, P, D, and F. Okay, so what are these subshells? These are basically places where the orbitals are found, and they have different shapes, which is why we did give them different names. The S subshell is spherical, so that's fairly easy to remember. It's not why it was originally called the S subshell, but that's how I remember it. It's a sphere-shaped shell, and sphere begins with S. The P subshell is dumbbell-shaped, and there's 3 different dumbbells that face in different directions. One is like basically in the x-axis, one's in the y-axis, and one's in the z-axis. So there's like 6 altogether. Three dumbbells or 6 lobes, which are kind of like the circular shapes of the dumbbell. Then we have the D subshell, which has a clover leaf shape, kind of like a 4-leaf clover with 4 lobes. And again, these lobes face in different directions, and one D subshell has all of these different lobes together. So it's quite a complicated shape. You can imagine if you superimpose those all on each other. And then the F subshell doesn't have shape associated with it or a named shape, but I think it looks a little bit like a flower, so that's what I called it. The cloverleaf, dumbbell, and spherical were named by other scientists. I came up with the flower, both because I think it looks a little bit like a flower, and also because flower begins with F, so that helps remember the name. You to remember the name. All right, so now that we've gone through all of that information about the subshells, we'll talk about orbitals, which are they're the mathematically defined space where an electron exists. However, it's like an orbital isn't like a single position in an atom or even a ring like a Bohr ring. It's more like a 3-dimensional space in which an electron can exist, but the electron may be in different parts of the orbital at different times. So if you look at this image here, this shows an S orbital, which would be in an S subshell. The likely location of electrons, and the more dense the dots, that's the higher probability that an electron will be found there. So they're more likely to be found towards the center, which kind of makes sense because that's close to the nucleus. And the negatively charged electrons want to be close to the positively charged nucleus, but they can also exist further out. So because the position of electrons is not precisely known, it's called an electron cloud. So this is like the official term for like how electrons are arranged, or like the probability of their being arranged. So this is an S orbital, so it's got a spherical shape. But if you look at the other orbitals, they'll have like more complex shapes. based on the shape of the subshell. Now, each orbital can hold up to 2 electrons. It can have 1 or 0, but it can't have more than 2. Okay, so each subshell has a specified number of orbitals. And again, they get increasingly complicated. The S subshell has 1 orbital. P has 3 orbitals. D has 5 orbitals, and F has 7 orbitals. Now, since now remember, each orbital, no matter which subshell it's in, can only hold 2 electrons. So since S has 1 orbital, it can hold 2 electrons. Since a P subshell has 3 orbitals, it can hold 6 electrons, because 2 times 3 is 6. A D orbital can hold, has 5 orbitals. 2 times 5 is 10, so it can hold 10 electrons. And an F subshell has 7 orbitals and can hold 14 electrons. Okay, so why are these subshells able to have different numbers of orbitals, and why are they able to hold a different number of electrons? An easy way to think about this is if you look at the shape. So on this slide, I'm showing the P subshell, which has that dumbbell shape. And you can imagine that each lobe of the dumbbell can hold 2 electrons. So this is 1 orbital within the P subshell. But then remember, there's 2 other dumbbells facing another direction. So this is a second dumbbell. And this is another orbital that can hold 2 electrons. And this is a third one that can also hold 2 electrons. All right, so this is like what it would look like all superimposed on each other. So that is like each one of those essentially holds 1 electron, so that's 6 altogether. So that is roughly what what those lobes mean. Now the spherical one can hold 2 electrons, so it doesn't have 2 lobes, but it still has an orbital that can hold 2 electrons. But it's like if you think of the lobes as being each one able to hold more than the last, that's like roughly like why each one is able to hold more electrons. Okay, so now we're going to go on to look at a little bit more detail in what these shells look like. Now, even though every single principal shell has an S subshell, they're not exactly the same. The N equals 1 is actually quite tiny. N equals 2 is a little bit larger. Each subshell is slightly larger than the last. And they also have these like funky little rings in the middle, which indicate like higher or lower probability of an electron being there. So they're not exactly the same, but they're similar. They're all sphere shaped, but they get larger and they have like a slightly funkier shape as you get larger. Okay, so we're going to take a little break from that, and then I'm going to describe electron configurations in more detail. An electron configuration is simply a written description of where electrons are located. So again, we'll start with hydrogen, our simplest atom. It's got 1 electron total, and it's in the first energy level, which only has an S subshell. So we write 1s1. This is the way scientists write this. So it's always in the same order, so that like if you look at an electron configuration that somebody else wrote, you know what it is. So the first one refers to the principal quantum number n. The S is the subshell, and then the number of electrons in the subshell is indicated by superscripts. So for hydrogen, it's 1s1.